Hello, and welcome back to The Sleepy Scientist. Whether you're here to drift off, to relax after a long day, or to simply let your mind wander among the stars, you're in exactly the right place. Tonight, we're setting course on a journey that began in the year 1977, when two tiny spacecraft left Earth with just enough fuel, instruments, and optimism to change the way we see the cosmos. They're still out there, quietly moving farther away than anything humanity has ever touched. This is the story of the Voyager missions, a tale of grand discoveries, poetic ambition, and the humble attempt to say hello to the universe. Now, before we begin, I have a small favour to ask. If you enjoy these sleepy explorations, a like and a subscribe mean more than you can imagine, especially to a spacecraft drifting on ancient radio waves and a creator whispering science into the night. And let me know in the comments where you're listening from, and what time it is where you are. Are you watching from a city that never sleeps, or a quiet village just settling down for the night? As always, I hope this video isn't too interesting, but if it is, and you find yourself wide awake, at least you'll be armed with some fascinating facts about interstellar space, magnetic fields, and cosmic mixtapes. So nestle in, breathe deep, and let's follow Voyager beyond the stars. This video is for educational and entertainment purposes only, and is not intended as medical advice. In the 1960s and 70s, Earth was buzzing, not with the hum of quiet contentment, but with the tension of a world caught between fear and fascination. The Cold War loomed like a fog over much of the globe, a standoff that never quite exploded but never really relaxed either. The United States and the Soviet Union eyed each other warily across oceans and ideology, racing not just to dominate geopolitics but to conquer the final frontier. And in that competition, something remarkable happened. Space became more than a military ambition. It became a canvas for imagination. In 1969, humankind set foot on the moon. It was an awe-inspiring moment, broadcast in flickering monochrome to millions of living rooms around the world. For a brief breath in history, the entire planet held its collective breath as Neil Armstrong and Buzz Aldrin bounced across the lunar dust. It was a peak moment, the climax of the Apollo program, and one of the few times in history when the words, "We did it," really meant all of us. But after that giant leap, something strange happened. Public interest in space started to wane. Once the moon was conquered, what was left? Going back again and again didn't hold the same sparkle. Budgets tightened. Missions were cancelled. NASA, having climbed the tallest mountain, now had to look around and ask, where do we go from here? They didn't have to look far, because out there, beyond the orbit of Mars, waited a collection of giants. Jupiter, Saturn, Uranus, Neptune. Worlds too distant to reach in the Mercury or Apollo days. Colossal, mysterious planets encircled by rings, cloaked in clouds, and orbited by strange moons. They were beautiful enigmas, and for decades they had remained just that, untouchable and mostly unseen. But now, with improved rocketry, better electronics, and a dash of confidence, they were finally within reach. Almost. There was just one problem. These outer planets are, quite frankly, staggeringly far away. Not just a little farther than Mars, we're talking hundreds of millions, even billions of miles. Sending a spacecraft to just one of them would be a challenge. Visiting all four? That was the kind of idea that made even optimistic engineers blink twice. But then, as if the universe had extended a friendly hand, an opportunity appeared. Or rather, it aligned. Quite literally. About once every 175 years, the outer planets line up in such a way that a single spacecraft can slingshot from one to the next using gravity assists. Think of it like a cosmic hopscotch, using the gravity of one planet to speed up and redirect the probe toward the next. This gravitational ballet wasn't new in theory, but the timing of this particular alignment, beginning in the late 1970s, was. If NASA wanted to pull off the greatest planetary tour in human history, the clock was ticking. They called it the Grand Tour, a mission concept born in the optimism of the 60s, It was originally a lavish, multi-probe idea with 4 separate spacecraft visiting the outer planets, and even Pluto. It was ambitious. It was breathtaking. It was also expensive. Too expensive. As the Apollo program wound down and congressional calculators began clicking, the grand tour was quietly shelved. But the dream didn't vanish. Instead, it adapted. Enter Voyager. A new, more modest concept that still aimed for greatness. Instead of multiple probes, NASA would launch 2 twin spacecraft with identical designs, slightly different trajectories, and just enough fuel and instrumentation to make history. They'd be robust, smart, and built to last, though no one at the time expected them to be operational for more than 5 years. The hope was simple: get them to Jupiter and Saturn. Anything more would be a bonus. And so, amidst disco music, bell-bottoms and rotary phones, work began on what would become the longest operating spacecraft in human history. Of course, nothing like this is ever simple. The 70s may seem quaint in hindsight, but building a spacecraft capable of surviving the harsh vacuum of space, and doing so with 1970s technology, was a monumental feat. These were the days when a digital watch was considered high-tech. The Voyager's computers had less processing power than a modern toaster. And yet, engineers found ways to make them brilliant in their simplicity and elegant in their design. Power was one of the first major challenges. Solar panels don't do much good when you're billions of miles from the sun, so the Voyager spacecraft would be powered by radioisotope thermoelectric generators, little nuclear batteries that converted the heat from decaying plutonium into electricity. Not exactly something you want to drop during transport. They were compact, efficient, and most importantly, they could last for decades. The spacecraft would need to communicate over vast distances. That meant a powerful antenna and a deep space network of enormous dishes on Earth ready to listen. The further the Voyagers travelled, the fainter their signal would become, eventually weaker than the noise of a TV tuned to static. And yet, those faint whispers would carry images, data, and even the soft sounds of Earth. But perhaps the most poetic piece of the project didn't come from an engineer. It came from a team of scientists, artists, and thinkers led by Carl Sagan. If we were going to send a spacecraft beyond the planets, maybe, just maybe, it would be found someday. Not by us, but by someone. An alien civilization. A curious mind from another world. What would we want to say? And so, the golden record was born. A phonograph disc made of gold-plated copper, carrying music, greetings in dozens of languages, sounds of Earth, and even brainwaves from a human in love. It was more than just a message. It was a declaration. We were here. This is who we are. As plans solidified and components came together, a quiet excitement spread through NASA's Jet Propulsion Laboratory. Unlike the splashy moon landings, the Voyager project was a slow burn. Less about heroism, more about endurance. These spacecraft wouldn't carry people, but they would carry everything humanity knew about spaceflight science and storytelling. In a way, the Voyagers became a time capsule, not just for extraterrestrial life, but for us. Built during a period of political division, economic inflation, and technological limitations, they still represented our best selves, our curiosity, our hope, our need to explore even when no one else is watching. It's worth remembering that in 1977, the idea of sending anything into interstellar space bordered on science fiction. The outer planets were mostly fuzzy dots in telescopes. No one had seen their storms up close or their moons in detail. Neptune was just a name. Titan was just a shadow. The edge of the solar system wasn't even well defined. And yet, there was an unshakable belief that we could get there, that with enough math, patience and duct tape, and perhaps a dash of luck, we could build something that would outlast us. Something that would keep going, even when we stopped listening. Something that would, in its quiet journey through the stars, carry the best parts of who we are. As the 70s rolled on and the launch window drew closer, teams worked day and night to prepare the twin spacecraft. Every wire was checked, every command coded. Scientists planned trajectories, artists selected images, engineers debated over thermal shielding and camera calibration. It was the space program's version of poetry and plumbing, data tables and daydreams. In the end, the Voyager missions weren't born out of triumph, but out of a longing, a need to keep reaching outward after we had already touched the moon. And maybe that's why they still resonate, because in a world filled with noise and distraction, the Voyagers remind us of something quieter, something enduring, the gentle, persistent pulse of curiosity that keeps asking, what's out there? And so, with fuel loaded, cameras ready, and the golden record secured in its protective case, the Voyagers stood poised on the launch pad. Twin time travellers, not destined to return, but destined to remind us what it means to leave. Designing something to last more than 40 years is ambitious under any circumstances. Designing something to survive for that long in deep space, with no repairs, no pit stops, and no second chances. That's not just ambitious. That's science fiction made real. Yet that was exactly what engineers at NASA set out to do when they began constructing the Voyager spacecraft in the early 1970s. The task was clear. Build 2 robotic explorers that could travel billions of miles through the solar system, study planets humanity had never seen up close, and then continue drifting into the unknown, transmitting data all the while. Easy, right? The first challenge was durability. Space is not a friendly environment. It's cold, like -400 degrees Fahrenheit cold, and it's filled with radiation, cosmic dust, and occasional bursts of charged particles that would make your phone cry. The Voyagers needed to be tough, not flashy or fast, just extremely, stubbornly durable. The outer shell of each spacecraft was built around a sturdy aluminum frame, designed to hold up under launch stress, cosmic debris, and decades of solar radiation. Protruding from that core were antennae, scientific instruments, booms, and the most iconic part, the big white high-gain dish antenna, a 3-meter wide structure that looked like a satellite TV dish, designed by someone with dreams of interstellar cable. That dish was key. It would be Voyager's voice, whispering data back to Earth across incomprehensible distances. Even now, decades later, Voyager's signal reaches us at a strength of less than a billionth of a watt, weaker than the static buzz from an old television set. But thanks to the massive dishes of NASA's deep space network, we can still hear those whispers from the edge of the solar system. Inside the spacecraft was an onboard computer system that, even by 1970s standards, wasn't exactly cutting edge. Each Voyager carried about 69 kilobytes of memory. That's not a typo. 69 kilobytes. For context, a single modern photo from your phone takes up several megabytes. Voyager's entire brainpower could be stored on one floppy disk with plenty of room to spare for a few recipes and a digital pet. Yet these humble electronics were carefully designed to be radiation-hardened, resilient, and simple enough to survive without human intervention. There were no flashy touchscreens or blinking lights, just solid-state logic, pre-programmed instructions, and long waits between commands. Each decision made by Voyager would take hours to execute, because round-trip communication could stretch to nearly a full day as the spacecraft moved farther and farther from Earth. Power was another major hurdle. Solar panels, the go-to option for satellites in Earth orbit, were completely useless once you passed Jupiter. Out there, sunlight is a whisper, not a shout, so engineers turned to something far more potent and long-lasting: radioisotope thermoelectric generators, or RTGs for short. These are compact power sources that use the heat from decaying plutonium-238 to generate electricity, a sort of nuclear campfire that keeps the instruments warm and the lights on. Each Voyager was equipped with 3 RTGs, which provided around 470 watts of power at launch. Over time, that output has decreased, But even now, more than 45 years later, they still provide enough energy to run a handful of critical instruments. Of course, engineers had to make hard choices about what could stay on and what had to be turned off as the power supply dwindled. It's a bit like managing an off-grid cabin with a failing generator. Do you keep the lights on or the fridge? Not both. Scientific instruments were carefully selected to maximize discovery while minimizing weight and power usage. Each spacecraft carried 10 main instruments, including imaging systems, spectrometers, magnetometers, plasma detectors, and cosmic ray sensors. The cameras, despite being far less powerful than the one in your phone, managed to capture some of the most iconic images in the history of space exploration, from Jupiter's swirling storms to Neptune's deep blue elegance. One particularly clever instrument was the magnetometer boom, a long extending arm that held sensors away from the spacecraft's own magnetic field. This allowed Voyager to measure the invisible lines of force stretching from planet to planet and, eventually, detect the subtle boundary of the heliosphere, where the solar wind gives way to the interstellar medium. Radiation shielding was also critical. Spacecraft electronics can be disrupted or fried by high-energy particles, especially near Jupiter, which has a magnetic field so strong it makes Earth's look like a refrigerator magnet. The design team had to encase sensitive components in protective materials and arrange them strategically inside the spacecraft's body to minimize exposure. They couldn't make Voyager invincible, but they could give it a fighting chance. Despite the sophistication of the design, there was also a certain elegance in its simplicity. Voyager wasn't built to land or return samples. It didn't need wheels or wings. It had no backup computer, no parachutes, and no way to fix itself. What it had was a rock-solid plan. Fly by, observe, transmit, repeat. Because of that focus, the mission team could dedicate their efforts to quality over redundancy. Every wire was checked, rechecked, and probably rechecked again. Every bit of solder was carefully placed. The spacecraft were assembled in clean rooms where stray particles and even human breath were controlled with the precision of surgery. When you're building a probe that will be farther from Earth than anything ever launched, perfection isn't just ideal, it's mandatory. Voyager's navigational system was another small miracle. The spacecraft used a combination of gyroscopes and star trackers to keep itself oriented in space. Unlike modern probes with real-time GPS-like systems, Voyager had to know where it was based on the stars, the sun, and the known positions of Earth and other planets. It would slowly pivot to take images, conduct experiments, and then realign itself to send data home. It was patient, methodical, and very polite about checking in. And then, of course, there was the matter of protection from cosmic debris. Even in the emptiest regions of space, a tiny pebble travelling at thousands of miles per hour can be deadly. Voyager was not armoured, but its most vital parts were tucked behind protective panels, and engineers calculated the risks of collisions to be very low. Still, every second the spacecraft survived was a small victory. Perhaps one of the most charming aspects of the Voyager design is how analog it is. Commands were loaded using sequences of binary code sent from Earth. Images were stored as strips of data and transmitted line by line, taking hours or even days to fully arrive. It's slow, yes, but it worked, and it still works. What makes the engineering story of Voyager so inspiring is not just its longevity, but how well it was built using the tools available at the time. There were no smartphones, no cloud computing, no CAD modelling like we have today. The team used pencils, paper and punch cards. They tested components using oscilloscopes and soldering irons. And yet, the spacecraft they created are still working, still talking, still listening, and they're still flying. Voyager 1 and Voyager 2 may be aging, but they remain humanity's farthest travelled emissaries. Their design wasn't flashy, but it was sturdy, smart, and filled with purpose. Each nut and bolt, each line of code was a vote of confidence in the idea that we could learn from our universe, even from very far away. As each year passes, the spacecraft grow quieter, their instruments dimmer, but they endure, drifting, humming, and sending back whispers of a vast cosmos that still waits to be explored. Voyager's design is a testament not only to good engineering, but to the simple belief that exploration matters even if no one's there to see it. In the late summer of 1977, 2 spacecraft stood quietly on separate launch pads in Florida, waiting for their moment to slip the bonds of Earth. They were identical in design, born of the same blueprint with the same mission stitched into their circuitry: to explore the outer planets of our solar system and keep going. They were called Voyager 1 and Voyager 2. Now you'd think Voyager 1 launched first. That would make sense, right? The first one is number 1. But space exploration doesn't always play by tidy numerical rules. In fact, Voyager 2 was launched first, on August the 20th, 1977. Voyager 1 followed just 16 days later, on September 5th. The numbering had nothing to do with the launch order. Instead, it was based on their planned trajectories and which would reach its target planets first. Voyager 1, despite launching second, was set to arrive at Jupiter and Saturn sooner than its sibling. So, numerically speaking, it would be the first to explore. A bit confusing perhaps, but hey. Naming conventions in space have always had a little poetic license. The fact that either spacecraft could do what they were set to do was, frankly, extraordinary. Because this wasn't just about sending a robot to one faraway planet. This was about visiting multiple planets in a single journey, a sort of planetary pinball game, where each encounter would fling the spacecraft onward with even greater speed. And all of this was made possible by a rare and beautiful bit of cosmic choreography, a planetary alignment that only happens about once every 175 years. During this rare configuration, the outer planets, Jupiter, Saturn, Uranus and Neptune, aligned in such a way that a spacecraft launched from Earth could use each one's gravity to slingshot toward the next. It's known as a gravity assist, and it's one of the cleverest tricks in the spaceflight playbook. Instead of using tons of fuel to reach the next planet, the spacecraft would steal a tiny bit of momentum from the giant planet it passed by. Not enough for the planet to notice, of course, but just enough for the spacecraft to pick up speed and change direction. Think of it like this. Imagine swinging around a moving train. As you latch onto it, you get tugged along and flung in a new direction, much faster than before. That's what Voyager did. Not once, but several times. But timing was everything. The planetary positions had to be just right. Too early or too late, and the opportunity would be lost. This meant the launch windows were tight and unforgiving. Each spacecraft had to launch within a specific time frame to hit its gravitational marks. Voyager 2, with a slightly longer and more complex route, had to go first. It would take a more leisurely cruise, aiming not only for Jupiter and Saturn, but potentially Uranus and Neptune as well, if it survived long enough. Voyager 1, on the other hand, had a faster, more direct path to Jupiter and Saturn, optimized for speed and early scientific returns. This is also why their paths diverged after Saturn. Voyager 1 took a sharp turn northward, away from the plane of the solar system, heading into the void above the planetary disk. Voyager 2 stayed more or less in line, continuing outward toward the 2 most distant gas giants. Their shared mission became a kind of tag-team exploration, each probe handing off the baton to the other as they moved farther from the Sun. The launch process itself was a marvel of engineering and patience. Both spacecraft rode atop Titan II-IE Centaur rockets, powerful multi-stage launch vehicles designed to push their precious cargo beyond Earth gravity well and set them on interplanetary trajectories. The launches went smoothly, with only a few nervous heartbeats along the way. Voyager 2's upper stage rockets suffered a brief data loss, but the spacecraft quickly stabilized. Voyager 1's launch was textbook, clean and precise. Within hours, both were en route to the stars, and from the moment they left the launch pad, they began something no other spacecraft had done before. They weren't just going to visit planets, they were going to ride a gravitational highway crafted by physics, precision timing, and a healthy dose of ambition. To fully appreciate how impressive this gravity assist technique is, it helps to look at the math, although don't worry, we'll keep it cozy. In essence, as Voyager approached a planet, it would fall into the planet's gravitational field, speeding up as it got closer. But instead of crashing or getting stuck in orbit, it would slingshot around the planet and exit the other side, now moving faster relative to the Sun. It's like robbing a bank where the bank doesn't mind and actually helps you out the door. This maneuver didn't just save fuel, it made the whole mission possible. Without gravity assists, Voyager would have needed an absurd amount of propellant to reach even a fraction of its destinations. Instead, it used the planets themselves as giant cosmic trampolines. The precision required to pull this off is mind-boggling. NASA's navigation team had to calculate the spacecraft's paths down to fractions of a degree. A tiny error in trajectory at Jupiter could mean completely missing Saturn, let alone the outer planets. And all of this had to be planned in advance, with no real-time steering once the flybys began. The Voyagers weren't remote-controlled RC cars, they were more like cosmic mail sent years in advance, with strict delivery instructions and no tracking updates. It's also worth noting that each flyby wasn't just about boosting speed. These were rich opportunities for science. Voyager would turn its cameras and sensors toward the passing planets and their moons, gathering data never seen before. But to do this, the instruments had to be reoriented, exposures timed, and commands sent long before the spacecraft reached its targets. Planning was done months ahead, with sequences of commands preloaded into the onboard computer like a carefully choreographed dance. As Voyager 1 raced ahead, it became clear it would be the first to leave the solar system's planetary neighbourhood. Its trajectory gave it a head start, but also meant it would not continue on to Uranus or Neptune. Voyager 2, while slower, had the potential to keep going, and eventually became the only spacecraft to visit all 4 outer planets. But neither path was guaranteed. In fact, the original mission plan only committed to Jupiter and Saturn. Everything beyond that? Optional. A bonus round. Incredibly, both spacecraft delivered, and then some. But back in 1977, none of that was certain. All NASA had were 2 carefully built probes, a fleeting planetary alignment, and a lot of hopes riding on a pair of rockets. The launches themselves might have looked routine. There were no astronauts waving from the gantry or dramatic countdowns broadcast to the world. But what they represented was profound. They were a quiet beginning to one of humanity's greatest journeys. The irony of it all is that the most far-reaching, most enduring space mission in history began with relatively little fanfare. Voyager didn't have the crowds of Apollo or the pageantry of a shuttle launch. It began with 2 silent liftoffs, a flurry of calculations and a belief that precision, gravity, and human ingenuity could get us to places we'd never been. And thanks to that rare planetary alignment, it worked. The timing was perfect, the slingshots aligned, and 2 small spacecraft were hurled into the grandest of tours. All because, once every century and a half, the solar system briefly opens a secret passageway, and someone had the good sense to take it. As Voyager approached Jupiter, it was like a moth drawing closer to a lighthouse made of swirling gas and crackling radiation. For decades, Jupiter had been the jewel of the solar system, a massive striped enigma spinning in the darkness. Astronomers had admired it through telescopes, marvelled at its size, and squinted at the blurry great red spot. But no one had ever seen it up close. Not really. Not until the Voyagers arrived. In March of 1979, Voyager 1 made its closest approach to Jupiter, passing within about 350,000 miles of the cloud tops, roughly the same distance between Earth and our own moon. Just a few months later, in July, Voyager 2 followed a similar path. Together they transformed Jupiter from a vague canvas of colour into a dynamic, living world. The first thing that struck scientists, and pretty much everyone else, was just how active Jupiter is. From a distance, its banded atmosphere looked almost serene. but as the spacecraft drew closer, the calm bands gave way to chaos. There were storms everywhere, swirling ovals the size of continents, jet streams roaring in opposite directions, and then, of course, there was the Great Red Spot itself, a storm so massive it could swallow Earth whole and still have room for dessert. This legendary feature, first observed more than 3 centuries ago, had long fascinated astronomers, but Voyager revealed it in stunning detail. It wasn't just red, it was textured, alive, moving, a swirling maelstrom of ammonia clouds and unknown chemistry, rotating counterclockwise with a speed that made hurricanes look like lazy whirlpools. And as it turned out, the red spot wasn't alone. Voyager captured dozens of smaller storms, dancing across the atmosphere in patterns too complex to untangle on sight. Jupiter's sheer size plays a big role in this drama. It's more than 11 times wider than Earth, and over 300 times as massive. Its atmosphere is a deep ocean of hydrogen and helium, layered with ammonia ice and shaped by intense rotation, so fast that a Jovian day lasts less than 10 hours. This rapid spin stretches the atmosphere into bands and fuels powerful storms that last for centuries. But the real surprises weren't in the clouds. They were in the company Jupiter keeps. Before Voyager, astronomers knew of a handful of Jupiter's moons, but they didn't expect much. Maybe a few icy rocks, maybe some cratered lumps like our own moon. What they got instead was a planetary family bursting with character. Let's start with Io, a moon that completely rewrote the rules of geology. Voyager 1's cameras captured something extraordinary. Plumes of material shooting up from Io's surface. Not mist or dust, but massive volcanic eruptions. Actual volcanoes on a moon. Active, angry, and unlike anything seen before. It was the first time an active volcano had ever been observed beyond Earth. These eruptions weren't minor. Some plumes shot hundreds of miles into space. The entire surface of Io was a chaotic mess of molten plains, sulfur lakes, and freshly formed lava flows. And the colours, oh, the colours! Yellows, reds, and oranges painted across a tortured landscape. It looked less like a moon and more like an alien pizza, bubbling and reshaping itself in real time. The reason for all this activity? Tidal heating. Io is caught in a gravitational tug-of-war between Jupiter and the nearby moons Europa and Ganymede. This constant squeezing and flexing generates heat deep inside the moon, melting rock and powering relentless volcanism. Earth's moon might serenely reflect sunlight, but Io was throwing tantrums in orbit. Then came Europa. At first glance it appeared calmer, a smooth, icy shell with very few craters, but smoothness in space is often a clue. It suggests the surface is being refreshed, perhaps by tectonics, or, in Europa's case, by something even more intriguing, a subsurface ocean. Voyager's images hinted at long, dark lines crisscrossing Europa's surface, not cracks in rock, but fractures in ice. These lines suggested the ice was floating on a liquid ocean, one kept warm by the same tidal forces that power Io's volcanoes. Beneath miles of frozen crust there might be a vast, salty sea, one that, to this day, remains one of the most promising places to search for alien life in our solar system. Ganymede and Callisto, 2 of Jupiter's other large moons, didn't want to be left out either. Ganymede turned out to be the largest moon in the entire solar system, even bigger than Mercury, and had hints of a magnetic field and grooved terrain. Callisto, ancient and cratered, wore its battered surface like a badge of honour, possibly untouched for billions of years. Each moon added a new chapter to Jupiter's story, and Voyager recorded every page with wonder. Back on the planet itself, the spacecraft also studied Jupiter's immense magnetosphere, a region of space dominated by its magnetic field, which is about 20,000 times stronger than Earth's. This magnetic field traps charged particles and creates intense radiation belts, far more dangerous than anything found near our own planet. Voyager had to be specially shielded just to survive the brief flyby. If you could see Jupiter's magnetosphere with your eyes, it would be bigger than the full moon in our sky, stretching millions of miles into space like an invisible glowing umbrella. Voyager also observed the auroras at Jupiter's poles, shimmering lights caused by particles spiraling along magnetic field lines and crashing into the atmosphere. These were similar in spirit to Earth's northern and southern lights, but on a much grander and more chaotic scale. One unexpected find was the faint dusty rings around Jupiter. Yes, rings. They're not as flashy as Saturn's, but Voyager detected them as subtle arcs of fine particles. These rings were likely formed from debris kicked up by micrometeorites smashing into small inner moons. They're thin, dark, and almost invisible, but they proved that Saturn wasn't the only ringmaster in the outer solar system. By the time Voyager 1 and Voyager 2 finished their Jupiter encounters, they had fundamentally changed how scientists thought about gas giants. Jupiter wasn't just a big ball of clouds, it was a complex, dynamic system filled with fascinating chemistry, ferocious weather, intense radiation, and an entourage of moons that could have headlined their own missions. What the spacecraft captured was not just a series of scientific data points, but an unfolding epic. They didn't just confirm what we suspected about Jupiter, they introduced us to things we never imagined. Volcanoes on other worlds, oceans beneath ice, moons that breathe fire, and moons that whisper secrets beneath their frozen shells. And all of it happened nearly 500 million miles away from Earth, relayed by machines with less computing power than a modern calculator, riding momentum and gravity through the vastness of space. The images they sent back, pixelated, grainy yet astonishing, sparked the imagination of scientists and dreamers alike. For the first time, humanity had peered deeply into the swirling face of Jupiter and seen more than just a planet. We saw a world of wonders, full of storms that never sleep and moons that defy expectation. A place that, even now, continues to surprise and delight, thanks to two little spacecraft that came for a flyby and ended up writing a new chapter in the story of the cosmos. If Jupiter was all drama and chaos, Saturn was its elegant cousin, graceful, photogenic, and wrapped in an outfit so iconic that even non-space nerds could spot it in a lineup. Its rings, gleaming like cosmic jewellery, had captured imaginations for centuries. Galileo saw them first in the early 1600s, though his telescope wasn't quite up to the challenge. He described them as ears on either side of the planet, an understandable misinterpretation. Over time, with better optics and more curious minds, those ears were revealed to be a spectacular system of rings, wide and flat and so perfectly thin it seemed they should not exist at all. By the time Voyager arrived in the early 1980s, Saturn had become the planet most often featured in science textbooks and sci-fi posters. But even the most detailed artistic rendering couldn't compare to what the spacecraft actually saw up close. The view was breathtaking. Saturn wasn't just beautiful, it was intricately detailed, mysterious, and full of surprises. Voyager 1 flew by Saturn in November of 1980, passing within 77,000 miles of the cloud tops. It provided humanity with its first high-resolution images of the ring giant, and they did not disappoint. Voyager 2 followed less than a year later in August of 1981, sweeping in for an even closer look. Between the two, we were granted an astonishing front-row seat to the greatest natural light show in the solar system. The rings were, of course, the stars of the show, made mostly of water ice ranging from tiny grains to house-sized chunks. The rings are vast, more than 200,000 miles across, yet astonishingly thin, often no more than 30 feet thick. That's like stretching a piece of paper across the length of an entire football stadium. How they stay so neatly arranged is still a subject of ongoing research and mild scientific head-scratching. Voyager's cameras peered into those rings and revealed far more than expected. They weren't just a few broad bands, but a delicate lacework of thousands of individual ringlets, with gaps, waves, and strange patterns that seem to defy easy explanation. One of the most prominent features is the Cassini division, a dark gap between the A and B rings that had been visible from Earth for centuries. But Voyager showed that the division wasn't empty. It contained its own set of thin, faint rings. Even more curious was the discovery of the Enki gap, a narrow division within the A ring, and the puzzling behaviour of so-called shepherd moons, tiny satellites whose gravitational influence helps maintain the sharp edges of the rings. These moons act like cosmic sheepdogs, corralling particles and sculpting the rings with invisible hands. It was as if the entire system was alive, shifting and responding in real time to the dance of gravity. The rings also exhibited something called spokes, which looked like ghostly radial lines drifting across the surface like shadows. Scientists still aren't entirely sure what causes them, possibly magnetic interactions with Saturn's rotating field, or tiny impacts creating brief clouds of particles. Whatever the mechanism, they gave the rings a haunted, almost ethereal quality. Saturn itself proved to be no less fascinating. Though less colourful than Jupiter, with a more uniform golden hue, its atmosphere was still active and dynamic. Bands of clouds flowed around the planet, driven by rapid rotation. A day on Saturn lasts just over 10 hours. Voyager observed jet streams, large storms, and curious hexagonal patterns near the poles, though the full mystery of Saturn's polar hexagon wouldn't be revealed until decades later by the Cassini mission. And then there was Titan. Of all Saturn's moons, and there are many, Titan stood out as the most intriguing. Larger than Mercury, shrouded in a thick orange haze, Titan was the only moon in the solar system known to have a dense atmosphere. Voyager's instruments detected that this atmosphere was mostly nitrogen, with traces of methane and other hydrocarbons. In fact, it was more similar to Earth's atmosphere than anything else found in space. But Voyager couldn't see through the haze. Titan was coy. It revealed its size, its pressure, and its chemistry, but not its surface. Still, scientists were captivated. An atmosphere that thick might mean weather, erosion, maybe even lakes or oceans. Speculation flourished. Was Titan a frozen Earth in slow motion, or a preview of what Earth might look like in 1 billion years? The questions lingered, unanswered, tantalizing. Voyager's flyby of Titan was actually one of the mission's most pivotal moments. In order to get a good look at the moon, Voyager 1 had to take a particular path, one that sent it out of the plane of the solar system after the encounter. It meant sacrificing a potential flyby of Uranus and Neptune. The trade-off was calculated, deliberate, and a little bittersweet. Titan had promised too much to ignore. Voyager 2, by contrast, skipped the Titan close-up and stayed in the solar system's main lane, preserving its route to the farther planets. This meant that while Voyager 1 ended its planetary tour at Saturn, Voyager 2 would go on to make history again. Still, Saturn gave both spacecraft more than enough to marvel at. Beyond the rings and Titan, the system was teeming with diverse moons, each with its own personality. There was Mimas, with a giant crater that made it look suspiciously like the Death Star. Tethys and Dione, with their bright surfaces scarred by icy cliffs and valleys. Enceladus, a small bright moon with a surface so reflective it looked like freshly fallen snow, and which, unbeknownst to anyone at the time, held its own geysers and subsurface ocean. Voyager didn't just show us these moons, it introduced them as characters in an unfolding story. Saturn's neighbourhood wasn't static. It was vibrant, strange, and deeply textured. The icy surfaces, the gravitational resonances, the whispered secrets buried beneath clouds. It all felt like an invitation to return. And Saturn itself, framed by its shimmering rings, became a symbol of space's quiet majesty. It wasn't the loudest planet, or the stormiest, or the most massive, but it was the one that made you stop and stare. The one that reminded us that beauty in the cosmos isn't just about power. Sometimes it's about grace. Voyager's visit to Saturn was brief in cosmic terms. just a few weeks of close encounters after years of travel, but in that time, it rewrote our understanding of the ringed planet and its many companions. It turned what was once a grainy point of light into a living world, rich with texture and wonder. And perhaps most impressively, it did all this with instruments designed in an era when the height of luxury was a shag carpet and a microwave oven. The spacecraft, by now many years beyond its warranty, had accomplished more than anyone had dared hope. With its job at Saturn complete, Voyager 1 bowed out, turning its antennas homeward as it began a new chapter, not as a planetary explorer, but as a Voyager in the truest sense. Its planetary tour was over, but its journey into interstellar space had only just begun. Saturn, with its golden rings and swirling moons, waved farewell in the rearview mirror, its mysteries partially unveiled, its beauty forever imprinted in Voyager's grainy yet unforgettable photographs. A planet that had once been a distant enigma was now a part of humanity's story, and Voyager had given it a voice. By the mid-1980s, Voyager 2 had already earned a glowing resume, up-close explorations of Jupiter's swirling chaos and Saturn's elegant rings. That alone would have made it a legendary mission. But Voyager 2 wasn't finished. It had one more rare opportunity to visit the two most distant planets in the solar system, Uranus and Neptune, the ice giants, the forgotten siblings in the planetary family photo. No other spacecraft had ever visited them, and to this day, no other has returned. Voyager 2 remains the sole emissary to these remote, chilly worlds. That's not just impressive, it's borderline heroic. First up was Uranus. Voyager 2 approached the seventh planet from the Sun in January of 1986. At first glance, Uranus looked simple, almost too simple. A pale turquoise orb, smooth and featureless, as if someone had drawn a planet with a single crayon and decided that was enough. But as always, Voyager's instruments peeled back the stillness and found complexity lurking beneath the calm. For starters, Uranus is tipped over. Most planets spin like tops, upright and wobbling slightly. Uranus spins like it's lounging on its side, rolling around the Sun with an axial tilt of about 98 degrees. No one knows for certain how it ended up that way. Maybe it collided with a massive object early in its history, or maybe it just likes to be different. Either way, this tilt has some strange consequences. Its seasons are extreme. One pole can face the Sun for over 20 years, basking in constant light, while the other is plunged into shadow. Then they swap roles. It's like an endless, slow-motion game of planetary sunbathing. At the time of Voyager's visit, the South Pole was pointed almost directly at the Sun, giving scientists a rare but oddly limited look at the planet's atmospheric dynamics. The atmosphere itself was colder than anything previously measured, a brisk minus 370 degrees Fahrenheit. Voyager detected faint cloud bands and signs of wind, though nothing as dramatic as Jupiter's storm systems. Later analysis would reveal that Uranus's apparent stillness was deceiving. It had winds of up to 500 miles per hour, but they were subtle, hiding beneath the haze of methane and ammonia. And then there was the magnetic field, a delightful curveball. Unlike Earth, which has a magnetic field neatly aligned with its rotation, Uranus said, "Let's do something weird." Its magnetic field is tilted nearly 60 degrees from its rotational axis and offset from the planet's centre. That means the magnetic poles don't sit at the geographic poles. They're scattered awkwardly off to the side. This creates a lopsided magnetosphere that wobbles and shifts as the planet spins. It's like a bar magnet trying to play hopscotch while rolling downhill. Voyager also got a close look at Uranus's moons, at least a handful that were known at the time. The spacecraft discovered 10 new ones, bringing the total to 15. Among the highlights was Miranda, a small, battered moon that looked like someone had tried to put a jigsaw puzzle together with pieces from 5 different sets. It had enormous cliffs, strange ridges, and deep, scarred valleys. Some of these features rose 12 miles high. That's more than twice the depth of the Grand Canyon. Scientists still aren't sure what caused its Frankenstein surface. It may have shattered and reassembled itself during a violent past, or it might have been shaped by internal tectonic processes. Miranda was small but unforgettable. It reminded everyone that moons are not just passive rocks, but often worlds in their own right, shaped by heat, gravity, and time. Then there were the rings. Yes, Uranus has rings too. Not as flashy as Saturn's, but distinct in their own way. Voyager found 9 dark, narrow bands orbiting the planet, composed of dust and rock. These rings are so faint that they weren't even discovered until the late 1970s, and Voyager helped confirm their structure and behaviour. They appeared almost invisible, made of particles coated with dark material that reflects very little sunlight. Cosmic stealth mode activated. After the Uranus flyby, Voyager 2 continued outward, heading for its final planetary target, Neptune. Another 5,000 million kilometres to go. That's more than 30 times the distance between Earth and the Sun. No pit stops, no tech support. Just a tiny aging probe coasting into the deep. In August of 1989, Voyager 2 arrived at the farthest planet in our solar system, at least by classical definition. Neptune, with its deep blue colour, looks strikingly beautiful. That colour comes from methane in its atmosphere, which absorbs red light and reflects blue. But unlike Uranus, Neptune wasn't shy. It was dynamic, vibrant, and full of surprises. Despite being farther from the Sun and receiving less light, Neptune turned out to be remarkably active. Voyager 2 discovered massive storm systems, including the now famous Great Dark Spot. This was a swirling oval storm roughly the size of Earth, complete with fast-moving winds and bright white clouds made of frozen methane. Winds on Neptune reached supersonic speeds, up to 1,300 miles per hour, and the fastest observed in the solar system. Exactly how Neptune generates such powerful weather, despite its cold and sparse energy input, remains a mystery. Like Uranus, Neptune's magnetic field was strange. Tilted and offset, it produced a magnetosphere that writhed and wobbled with each rotation. Voyager's instruments picked up intense radio emissions and evidence of complex interactions between the planet and the solar wind. It was as if Neptune, from its distant perch, was playing its own chaotic symphony in a key no one had heard before. And then came Triton, Neptune's largest moon and arguably one of the most fascinating objects in the outer solar system. Triton orbits in the opposite direction of the Neptune's rotation, a strong clue that it was likely a captured object, perhaps a Kuiper Belt wanderer ensnared by Neptune's gravity. Triton was cold, strange, and unexpectedly active. Voyager 2 saw geysers erupting from its surface, nitrogen gas spouting several miles high from beneath a thin crust. This cryovolcanism hinted at internal heat, perhaps driven by radioactive decay or residual tidal forces. The surface itself was marked by curious patterns, smooth plains, ridges, and dark streaks, unlike anything seen elsewhere. Triton even had a thin atmosphere of nitrogen, making it the only large moon besides Titan with a detectable envelope of gas. All in all, Voyager 2 discovered 6 new moons and a faint ring system around Neptune. These rings, like Uranus's, were dark and incomplete, with clumpy arcs rather than full continuous bands. It seemed the farther out you went, the more eccentric the rings became. The Neptune flyby marked the end of Voyager 2's planetary tour. It was the last time any spacecraft would see a new planet up close, at least so far. After that, Voyager turned its cameras away and settled into the next phase of its life, interstellar drift. But what it left behind was remarkable. Uranus and Neptune had gone from distant blue dots to real, complex worlds. Moons with geysers, storms faster than sound, magnetic fields that danced like drunken tops, and a reminder that even at the edge of the solar system, nature never stops surprising us. Voyager 2 didn't just extend the mission, it redefined what was possible. It taught us that the most remote places can hold the richest stories. if we're willing to go far enough to hear them. And sometimes, if you're very lucky and very precise, a little probe launched in the disco era can rewrite the encyclopedia from 3 billion miles away. Long before Spotify playlists or viral videos, humanity made a mixtape, not for each other, but for the stars. It was called the Golden Record, and it's currently sailing through interstellar space on board both Voyager spacecraft, waiting for someone, or something, to find it. If it sounds like the plot of a poetic science fiction story, that's because it kind of is. But this one is absolutely true. The Golden Record was the brainchild of a small imaginative team led by astronomer Carl Sagan. At the time, the Voyager missions were already ambitious, exploring the outer planets, travelling further than anything ever launched. But Sagan and his colleagues saw an opportunity to add something more, something human. If the spacecraft were going to leave the solar system entirely, they reasoned, why not attach a message? A greeting in case an alien civilization encountered it in the far future. Of course, the odds of that happening were microscopic. Voyager was tiny, the galaxy was enormous, and the distances were almost unfathomable. But that wasn't the point. This wasn't about likely contact. It was about the gesture. The result was a 12-inch gold-plated copper disc, an actual phonograph record, carefully engraved and encased in an aluminum jacket, along with a stylus and symbolic instructions on how to play it. Think of it as a time capsule, art project, an interstellar ambassador all rolled into one, and it had to represent, in just over an hour, the entire essence of life on Earth. No pressure. The team behind the Golden Record worked quickly. They had only a few months to gather content, decide what to include, and physically produce the discs in time for launch. Despite the tight deadline, they approached the project with care, humour, and a deep sense of wonder. They weren't just scientists, they were curators of human experience. One of the most iconic features of the record was the collection of greetings, spoken messages in 55 languages, ranging from Akkadian, a language of ancient Mesopotamia, to Wu, a Chinese dialect. Some were formal, others warm and playful. There's a greeting in English that says "Hello from the children of planet Earth." It's delivered in the small, clear voice of a child, simple, sincere, and strangely moving. But the team didn't stop with greetings. They included a vast array of natural sounds from our planet. These weren't just academic choices, they were deliberately emotional. The record contains the roar of surf, the rustle of wind, thunder, the calls of birds, the laughter of children, the sound of a kiss, and even the whoosh of a Saturn V rocket lifting off. One particularly haunting addition is the song of a humpback whale, eerie and beautiful, echoing across cosmic silence. Then came the music, and this part really was a mixtape. The record holds 90 minutes of carefully selected music from around the world, intended to showcase both diversity and unity. The selections include a Bach Brandenburg concerto, a gamelan piece from Indonesia, a Navajo night chant, a Japanese shakuhachi composition, a Peruvian wedding song, and Louis Armstrong's Melancholy Blues, among many others. There's also a track from Blind Willie Johnson called Dark Was the Night, Cold Was the Ground, a blues recording filled with wordless moans. Carl Sagan described it as expressing the human condition better than any spoken language could. And he had a point. Sometimes pain, longing, and hope are best carried by melody alone. Interestingly, the Beatles wanted to include one of their songs, Here Comes the Sun, but rights issues prevented it from being used. Even the Golden Record wasn't immune to copyright law. Perhaps a good reminder that bureaucracy truly is a universal language. In addition to the audio, the record contained a collection of 116 images encoded in analog format. These included photographs and diagrams meant to introduce whoever found the record to our planet and species. There were pictures of landscapes, animals, human anatomy, people eating and dancing, a mother nursing her child, and even a photo of Earth from space. There were also scientific and mathematical diagrams, pulsar maps, DNA structures, and units of measurement, designed to give the finder some frame of reference. If an alien civilization were able to decode the record, they might be able to piece together a sense of where we are, what we look like, and how we think. One of the most poetic and personal inclusions was a set of brain waves, specifically the neural activity of Andruyan, a member of the production team who later became Carl Sagan's wife. For an hour, electrodes recorded her thoughts as she meditated on a wide range of ideas, including the history of Earth, the nature of humanity, and falling in love. That brainwave data was then encoded into the record, like a mental fingerprint frozen in time. Somewhere in deep space, Anne's thoughts continued to travel, a heartbeat of human consciousness reaching into the dark. All of this was accompanied by instructions on how to play the record. These were etched onto the cover in symbolic language, mathematical and scientific notations that, it was hoped, a sufficiently advanced civilization could decipher. There's even a stylized drawing of how to assemble the included needle and spin the record correctly. It's like an IKEA manual for aliens. And yes, the record also includes the location of Earth, based on a map of pulsars and their relative timing. Some have joked that we basically told the galaxy where to find us, but Sagan saw it differently. He believed that any species advanced enough to reach the record would be able to decide for themselves whether they came in peace. The record was not a flare or a beacon, it was a greeting card. In total, 2 copies of the Golden Record were made, one attached to each Voyager spacecraft. They are the most distant human-made objects in existence, and they carry with them this golden time capsule, spinning silently through the stars. It's easy to dismiss the project as a romantic gesture, and in many ways it was. But it was also deeply practical. It reminded us that space exploration isn't just about rocks, orbits, and radiation belts. It's also about meaning, about sending not just our machines but something of ourselves into the cosmos. Carl Sagan once said that the record was a bottle cast into the cosmic ocean. It might never be found, and if it is, it might not be understood. But the act of sending it, the choice to represent our species with music, laughter, and the sounds of whales, was a statement of who we are at our best. It's comforting in a strange way to know that somewhere, billions of miles from here, our little golden disc is still flying. It's not broadcasting, it's not blinking or beeping, it's simply there, turning slowly, gently, forever. A quiet promise that we were here, that we made music, that we looked up and wondered, and that we said hello. When Voyager 1 and Voyager 2 left Earth in 1977, we knew our solar system in broad strokes. We had a few up-close images from earlier missions, a lot of telescope observations, and a heap of educated guesses. The outer planets were still shrouded in mystery, enormous, distant, and faintly understood. But Voyager changed all of that. It didn't just take better pictures or fly a little farther. It turned question marks into exclamation points and rewrote entire chapters of planetary science. Let's start with the moons, because wow, did the moons put on a show. Before Voyager, many of these satellites were thought to be little more than cold, cratered rocks, dead worlds, but they turned out to be anything but dull. Take Io, for example. No one expected a volcanic powerhouse orbiting Jupiter, yet Voyager 1 captured enormous plumes erupting from its surface, the first active volcanoes ever seen beyond Earth. These weren't just occasional burps of lava either. They were massive geysers, spewing sulfur and other materials hundreds of miles into space. The surface of Io looked like something out of a surrealist painting, mottled in yellows, reds, and oranges, shaped by constant renewal and violent upheaval. It was alive, geologically speaking, in a way that had never been imagined. Then there was Europa, also orbiting Jupiter. At first glance, it was the quiet, icy sibling to Io's volcanic frenzy. But Voyager's close-up images revealed a surface crisscrossed with dark lines, fractures, likely caused by a shifting, cracking ice shell. beneath that shell, scientists began to suspect might be a liquid ocean, an ocean heated by tidal forces, an ocean that, even today, holds the tantalizing possibility of life. Before Voyager, Europa was just another dot in the sky. Afterward, it became one of the most intriguing places in the entire solar system. Saturn's moons had their moments too. Enceladus looked like a snowball, smooth, bright, and surprisingly young. The lack of impact craters suggested ongoing resurfacing, hinting at internal activity. Although it wasn't until later missions that geysers were confirmed, Voyager gave the first clues that Enceladus was more than just a frozen pebble. And then there was Titan, Saturn's largest moon. Voyager couldn't see through its dense orange haze, but it could measure it. That thick atmosphere, mostly nitrogen with a dash of methane, was denser than Earth's. It was the only moon with a substantial atmosphere, and one with chemistry eerily reminiscent of early Earth. Titan quickly graduated from big moon to serious candidate for prebiotic chemistry. Out past Saturn, Voyager 2 introduced us to Uranus and Neptune, and more unexpectedly complex moons. Miranda, orbiting Uranus, looked like it had been shattered and reassembled with spare parts. Triton, Neptune's largest moon, had active geysers of nitrogen and a retrograde orbit, suggesting it had been captured from the Kuiper Belt. And the moons weren't the only stars of the show. Voyager also took a long, hard look at the planets themselves, stripping away decades of assumptions. Jupiter, of course, was stunning. We had known about the Great Red Spot for centuries, but Voyager showed it in motion. A gigantic storm system swirling with mesmerizing elegance. Even more surprising was just how dynamic the entire atmosphere was. Jet streams, smaller storms, and layers of colourful clouds all moving at astonishing speeds. Jupiter wasn't a placid gas ball, it was a weather machine on a scale too big to imagine. Saturn, graceful and golden, had its own complex atmospheric bands and storms. Voyager revealed faint wisps of cloud patterns and uncovered the presence of lightning and auroras. The planet's shape, flattened at the poles due to its rapid rotation, was captured in detail, adding depth to our understanding of how such massive worlds behave. And the rings. Oh, the rings. Voyager turned Saturn's rings from a pretty celestial accessory into a scientific playground. It showed that the rings were made up of countless smaller ringlets, each sculpted by gravitational interactions. There were spokes, temporary, ghostly features that drifted across the rings like shadows, and gaps, like the Cassini division, that weren't truly empty, but filled with fainter rings and tiny shepherd moons. These moons helped maintain the structure of the rings, using their gravity like a broom to sweep and shape the icy debris. Even Jupiter, Uranus, and Neptune, all previously thought to be ringless, turned out to have ring systems of their own. Jupiter's were faint and dusty. Uranus's were thin, dark, and sharply defined. Neptune's rings had mysterious arcs, incomplete segments that defied expectations. Before Voyager, Saturn was the only ring bearer. After Voyager, rings became the rule rather than the exception. And then there were the magnetic fields. Voyager brought magnetometers, instruments that could measure magnetic strength and orientation. What they found was bizarre and beautiful. Jupiter's magnetic field was immense, stretching millions of miles into space. It trapped particles and created radiation belts far stronger than Earth's. This magnetosphere was a bustling region, full of charged particles, electrical currents, and constant activity. Saturn's magnetic field was more symmetrical, almost aligned with the planet's rotation axis, but still powerful. Voyager detected radio emissions and auroras, along with interactions between the rings and the magnetic environment. Uranus and Neptune, though, really flipped the script. Their magnetic fields were tilted and off-center, giving rise to wobbling, lopsided magnetospheres. These weren't just curiosities, They were puzzles that forced scientists to rethink how planetary magnetic fields are generated. Perhaps internal structures, rotation, and convection were more diverse than previously believed. Voyager showed that magnetic fields weren't all built the same way. Each planet had its own electromagnetic personality. Atmospheric studies added more layers of understanding. Voyager used spectrometers and infrared sensors to analyze the composition of planetary atmospheres, measuring temperature, cloud height, and chemical makeup. These data helped confirm the presence of hydrogen, helium, methane, and other trace gases. But more than that, they revealed how light and heat interacted across billions of miles, offering insights into planetary climates that hadn't been imagined. Even the faintest whiffs of data had meaning. Tiny variations in gravity revealed differences in planetary mass distribution. Plasma detectors measured the solar wind's interaction with planetary magnetospheres. Voyager collected data that fed into thousands of scientific papers, some still being written decades later. And let's not forget the new moons, dozens of them. Before Voyager, the outer planets had just a handful of known satellites. Afterward, their moon counts more than doubled. These weren't just dots on a chart. They were real places, each with a story, a history, and a unique geology. All of this came from spacecraft with less computing power than a pocket calculator, relying on analog systems and tape recorders. Voyager didn't have fancy sensors or adaptive software. What it had was resilience, elegance, and an extraordinarily well-thought-out design. But perhaps the most important thing Voyager revealed wasn't a single storm, moon, or magnetic quirk. It was the overall complexity and richness of the solar system. The missions shattered the idea that the outer planets were dull gas balls and their moons lifeless ice cubes. Instead, we found worlds in motion, changing, erupting, spinning, cracking, and reshaping themselves across cosmic time. Voyager didn't just show us what was out there. It reminded us how little we truly knew. It opened doors. It inspired questions we hadn't thought to ask. It gave us not just data, but a sense of wonder sharpened by detail. From volcanic moons to tilted magnetic fields, from rings within rings to dark spots on distant planets, Voyager transformed our solar system from an abstract diagram into a vibrant, evolving family of worlds. It proved that exploration, even done slowly and quietly, can change everything. And the best part, Voyager is still out there, listening, still drifting, still teaching us how much more there is to know. By the year 1990, Voyager 1 had completed its primary mission. It had flown past Jupiter and Saturn, snapped its stunning images, and helped rewrite the textbooks. Afterward, it continued outward into deep space, drifting silently beyond the orbit of Neptune. Most spacecraft, once their cameras were turned off, simply faded from public view, out of sight, out of mind. But Voyager wasn't quite done yet. Not because it had more science to perform, though it did, but because it still had one more picture to take. A picture that wasn't about planetary rings or volcanic moons. It was about us. The idea was simple in concept, but bold in spirit. Turn Voyager's cameras back toward Earth and take a snapshot from the edge of the solar system. A family portrait of sorts, the Sun and its planets seen from billions of miles away. It was Carl Sagan, ever the poetic advocate for cosmic perspective, who pushed hardest for the idea. He had long believed that such a photograph could offer a rare and powerful moment of reflection, a visual reminder of our small place in the universe. There was some resistance to the plan. Engineers were understandably cautious. Voyager's cameras weren't designed to point near the Sun, even from that distance, and a misstep could have damaged sensitive equipment. But by 1990, the risk was minimal. The cameras were already being retired from regular use. So on February 14th of that year, Valentine's Day, NASA gave the go-ahead. Commands were sent, the spacecraft rotated, and the shutter clicked. The result was not particularly dramatic at first glance. In one of the images, Earth appeared as a tiny, pale blue dot, less than a pixel wide, caught in a shaft of scattered sunlight. It floated against the darkness of space, almost lost in the static. If you didn't know what you were looking at, you might have missed it entirely. But when you understood what you were seeing, it became one of the most profound photographs ever taken. That faint speck was Earth, home, everyone you've ever known, every civilization, every story, every joy and every sorrow, all contained within a single shimmering mote of light. From nearly 4 billion miles away, our planet was reduced to a whisper. Carl Sagan later reflected on this image in what became one of the most moving passages in the history of science communication. In his book, Pale Blue Dot, he wrote, "Look again at that dot. That's here, that's home, that's us." And then he expanded on what that dot contained. Every king and peasant, every mother and father, every hopeful child, every conqueror and coward, every teacher of morals and corrupt politician, every superstar and every saint, all of them, all of us, on that pixel. Sagan's words were not just poetic, they were pointed. He reminded us of the folly of human arrogance, the endless battles we fight over borders and ideologies, the importance of kindness, of preserving our fragile planet, of recognizing that from a cosmic perspective, we are all riding the same speck of dust through an indifferent universe. That photograph, taken from the edge of the known solar system, became a mirror held up to humanity, not to show us our grandeur, but our fragility. Interestingly, Earth wasn't the only object captured in that portrait. Voyager's cameras also snapped images of Neptune, Uranus, Saturn, Jupiter, Venus, and even the Sun itself. Mercury was too close to the Sun to be seen, and Mars didn't show up well due to the angle and glare. But Earth, that pale blue dot, stole the show. Technically speaking, the image was part of a series known as the Solar System Family Portrait. It was composed of 60 images stitched together, covering a span of more than 32 degrees of the sky. Each image was carefully planned, each angle calculated. And once the images were taken, the cameras were powered off for good. Voyager would continue collecting scientific data with other instruments, but it would never take another photograph. In that way, the pale blue dot image was Voyager's farewell, not just to the planets it had visited, but to visual observation itself. A final look back, a gentle turning of the gaze before heading into the long silence of interstellar space. And what a look it was! The blue colour of Earth in the image comes from Rayleigh scattering, the same phenomenon that makes the sky blue when we look up from the ground. It's caused by the way molecules in the atmosphere scatter sunlight. Even from billions of miles away, that soft blue tint is visible. It's the colour of oceans and sky, of breathable air and liquid water, subtle clues that this particular speck might be special. But the image also captures the loneliness of space. There's no parade of lights, no flags or flares, just a pinprick in a vast black sea. That emptiness, far from being depressing, is actually kind of freeing. It strips away the noise and reminds us what really matters. Not territory or titles, not noise or pride, but connection, curiosity, the desire to understand our world and our place in it. Voyager had seen Jupiter's storms, Saturn's rings, Uranus's tilt, Neptune's winds, and the many strange and wonderful moons along the way. But in that one moment, it turned its gaze inward, not to the machinery of space, but to the poetry of it. And with that, it gave humanity a gift that no other mission had offered: perspective. It's easy in day-to-day life to lose sight of the big picture, to get caught up in small dramas and deadlines, but every now and then, a single pixel can change how we see everything. That was the power of the pale blue dot. It didn't just show Earth, it reminded us to cherish it. Voyager 1 didn't need to take that image. Its scientific mission was already over. The camera system was soon shut down permanently. But that photograph, and the reflection it inspired, became one of the most enduring legacies of the entire mission. It's still out there, that little spacecraft, still moving farther away, still whispering data back to Earth, and Earth still spinning, still dreaming, still tucked inside that pale dot. In the end, the pale blue dot wasn't just a photo, it was a reminder that even in the vastness of space, a tiny world can hold infinite meaning, and that maybe, just maybe, looking back from a great distance helps us see what's right in front of us a little more clearly. If the solar system were a house, we'd live somewhere in the living room, comfortably close to the warmth of the sun, surrounded by familiar planets, with a nice view of the asteroid belt and the gas giants just beyond. But like any house, there's a boundary, a point where the home ends and the wilderness begins. For Voyager 1, that point was something called the heliopause, and crossing it marked one of the most important milestones in the history of human exploration. Now, to understand what the heliopause is, it helps to picture the sun not just as a glowing ball of light, but as a sort of cosmic campfire, sending out not only light and heat, but a stream of charged particles known as the solar wind. This solar wind blows outward in all directions, forming a massive bubble around the solar system. That bubble is called the heliosphere. Inside the heliosphere, the sun is in charge. Its magnetic field shapes the space environment, its particles fill the void, and everything dances to its tune. But eventually, that influence runs out. The solar wind weakens as it pushes against the material between the stars, a cold, sparse mixture of gas, dust, and cosmic rays known as the interstellar medium. The heliopause is the boundary where the solar wind strength finally gives way. It's the outer skin of the sun's protective bubble. Beyond that, the interstellar medium takes over, and beyond that, well, that's interstellar space. This may sound tidy in theory, but in practice it's messy. There's no glowing sign that says you are now leaving the solar system. It's more like a shifting, wobbly, invisible frontier, constantly changing depending on the solar cycle, local density, and magnetic conditions. Scientists had long predicted where the heliopause might be, but no one had ever visited it, until Voyager. In August of 2012, NASA made an extraordinary announcement. Voyager 1 had crossed the heliopause and entered interstellar space. It was the first human-made object to do so. After more than 35 years of travel, it had officially left the sun's domain. But how do you know when you've crossed such a boundary, especially when you can't see it? You don't just open a door and step outside. What Voyager did instead was detect changes in its environment. One of the biggest clues was in the particles around it. Inside the heliosphere, the spacecraft was surrounded by solar particles, energetic protons and electrons thrown off by the sun. But as Voyager moved outward, it began to detect a drop in those solar particles and a simultaneous increase in cosmic rays, high-energy particles coming from outside the solar system. That was a major red flag, or, in this case, a green light. Then came the magnetic data. Scientists expected the direction of the magnetic field to shift dramatically once Voyager entered interstellar space, but that didn't happen immediately. The field changed subtly, but not in the way models had predicted. This led to some spirited debate. Had Voyager crossed the boundary or not? The answer came in the form of a lucky solar outburst. In March of 2012, the Sun had released a coronal mass ejection, a huge wave of charged particles, which eventually caught up to Voyager more than a year later. When that shockwave reached the spacecraft in April of 2013, Voyager's instruments recorded a sudden oscillation in the surrounding plasma, allowing scientists to measure the density of the space around it. What they found was striking. The plasma density had jumped by a factor of 40, indicating that Voyager was now in a much denser region, the interstellar medium. That sealed it. The spacecraft had truly crossed the heliopause. It's worth noting that while Voyager 1 entered interstellar space, it didn't leave the solar system entirely. The Sun's gravitational pull extends far beyond the heliopause, past the Kuiper belt and deep into a distant region known as the Oort cloud. That cloud, a theoretical shell of icy bodies, could stretch halfway to the nearest star and may be home to the seeds of long-period comets. Voyager, moving at more than 38,000 miles per hour, won't reach the inner edge of the Oort cloud for another 300 years. It won't exit it for another 30,000. So, yes, technically it's still within the Sun's gravitational neighbourhood, but it's beyond the Sun's influence in every other way. Voyager 2 followed its sibling into interstellar space in November of 2018. Although it took a different route and encountered slightly different conditions, it provided valuable confirmation of Voyager 1's findings. For the first time, we had not one, but two data points from the edge of the Sun's domain, a rare opportunity in a science where single missions are usually all we get. Crossing the heliopause didn't reveal dramatic new landscapes or glowing interstellar clouds. There were no space whales or alien billboards. But what Voyager found was, in its own quiet way, profound. The interstellar medium is colder, denser, and more complex than previously imagined. It hums with low-frequency waves and is shaped by magnetic forces that reach across light years. And perhaps most poignantly, the crossing marked a symbolic boundary as much as a scientific one. Voyager had officially gone from being a planetary mission to being a galactic one. It had become an interstellar traveller. In many ways, this was the fulfillment of a dream going back centuries. Humans have always imagined travelling to the stars, but Voyager 1 is the first to actually do it. Not quickly, not glamorously, but steadily, faithfully, and without a return ticket. It's not headed to any particular star. Its trajectory will take it slowly through the Milky Way, perhaps passing within a few light years of a distant sun in 40,000 years. By then, Earth's continents will have shifted, languages will have changed, and Voyager's signal will have long gone silent. But the spacecraft will still be out there, intact, drifting between stars, a tiny piece of human craftsmanship sailing through an unimaginable sea. And it's still talking to us, faintly, patiently, a signal so weak that it takes more than 17 hours to reach Earth. But it comes through, a whisper from beyond the sun, telling us about magnetic fields and particle density and the subtle nature of the interstellar breeze. Crossing the heliopause didn't make front-page news for long. There were no parades or fireworks, but it was one of the most important thresholds humanity has ever crossed. It marked the beginning of a new chapter, not just for space exploration, but for how we see ourselves. Voyager left the warmth of the solar bubble and entered the cold, quiet dark, and it kept going. That perseverance, that curiosity, that quiet push beyond every horizon, it's hard not to see it as a reflection of something deeply human. A part of us left the solar system, and it hasn't looked back. More than 4 decades after launch, the Voyager spacecraft are still going. They don't make headlines like they used to. They aren't snapping dramatic photos or soaring past new worlds, and yet, even now, these twin explorers continue their long, lonely journey outward, slipping further into the great unknown, while their faint voices still reach us across the cosmic silence. Voyager 1, the faster and farther of the two, is currently more than 15 billion miles from Earth. To put that in perspective, light itself, the fastest thing in the universe, takes over 22 hours to travel from Voyager 1 back to us. It's the most distant human-made object in existence, and unless something else catches up, it always will be. Voyager 2 is a little behind, travelling in a different direction, at a slightly slower speed, but not by much. It's currently around 12.5 billion miles from Earth and catching cosmic particles as it sails through interstellar space. At those distances, nothing is easy. Communicating with either spacecraft is a delicate dance of timing, calibration, and hope. NASA's Deep Space Network, a global array of enormous radio antennas, listens day and night for Voyager's faint signal, and faint is an understatement. By the time their transmissions reach Earth, they're about 10 billion times weaker than the power needed to operate a digital wristwatch. Detecting them is like picking up the gentle ping of a cell phone from another planet, if the planet was on the other side of the solar system. Despite the distance, they are still talking to us. Not loudly, not quickly, but consistently. Their signals arrive in a whisper of ones and zeros, patiently spelling out data that helps scientists learn about the space beyond our solar bubble. But these spacecraft are getting old and tired. Each Voyager was designed to operate for about 5 years. 5 years, that was the plan. Just enough time to make it to Jupiter and Saturn, send back some photos, and retire with honour. But they've kept going for nearly 50 years, far beyond their original expectations. Of course, they've had to make sacrifices to stay functional. Their power sources, radioisotope thermoelectric generators, or RTGs, work by converting heat from decaying plutonium into electricity. When they launched in 1977, each spacecraft generated around 470 watts. Today they produce less than half of that. The drop is slow but steady, and the math is unavoidable. Less power means fewer systems can remain on. Over the years, mission controllers have had to make tough choices. They've shut down heaters, turned off backup systems, and selectively powered down scientific instruments. Every decision is like managing a dimming lantern on a cold night. You can only keep so many parts warm before something has to go dark. As of now, each spacecraft has a handful of instruments still running. They can no longer take pictures. The cameras were turned off decades ago to conserve energy and bandwidth, but they can still measure things. Magnetic fields, charged particles and plasma waves. And that data is invaluable. Voyager is the only mission giving us direct measurements from the interstellar medium, a region we've never visited before. The environment out there is very different from the sunlit regions we know. There are no planets, no rings, no moons, just vast emptiness punctuated by cosmic rays, drifting atoms, and the occasional shock wave from a distant solar flare. The density of plasma is higher than expected, and the magnetic fields are behaving in ways that are both fascinating and a little puzzling. Voyager is helping us understand how our sun interacts with the rest of the galaxy, and how the edge of the solar system blends into everything beyond. Even at these incredible distances, the spacecraft remain surprisingly healthy, all things considered. Their main computers, built in the era of disco and floppy disks, are still functioning. The same redundant programming systems that once aimed cameras at Jupiter's moons are now carefully regulating their thermal balance and signal timing. Occasionally, a glitch occurs, a command gets garbled, a system hiccups. But engineers at NASA's Jet Propulsion Laboratory, many of whom weren't born when Voyager launched, know how to coax the spacecraft back into line. In 2020, Voyager 2 experienced a communication blackout after a planned maintenance event on the Earth-based antenna in Canberra, Australia, the only dish capable of talking to it due to its position in the southern sky. When the antenna came back online after 8 months, Voyager 2 responded, faint, steady and right on cue. After over 12 billion miles and 43 years, it still remembered its instructions. That's impressive behaviour for any technology, let alone one operating far beyond the design limits of its time. In recent years, engineers have had to get creative to keep things running. In 2023, Voyager 1 began sending back corrupted data. Months of patient detective work eventually led to a solution. Engineers deduced that a single faulty memory chip had likely gone bad. They crafted a workaround, a kind of cosmic software patch, and beamed it across the stars. It took over a day for the signal to arrive, and another day to confirm success, and it worked. Each fix is a minor miracle, each transmission is a small triumph. Of course, the end is inevitable. At some point in the next few years, the remaining instruments will be shut off one by one. The power will dwindle to the point where even the radio transmitter can no longer function. When that happens, the signal will fade and Voyager will go silent. Not because it failed, but because it succeeded far longer than anyone thought possible. And yet the spacecraft won't stop. They will keep travelling at over 35,000 miles per hour. Long after they fall silent, long after Earth loses contact, Voyager 1 and Voyager 2 will continue their journey. In about 40,000 years, Voyager 1 will pass within a light year or two of a small star called Gliese 445. Voyager 2 will drift in a slightly different direction. not approaching any known star for perhaps even longer. They're not on a collision course with anything, just quiet, eternal travellers in the dark. And they still carry their golden records, time capsules etched in gold containing music, greetings, and the sounds of Earth. If some distant civilization ever finds them, they'll discover a tiny artifact of our species, a message from a long-gone world saying, "We were here." For now, though, the Voyagers are still very much with us. Their signals still reach the Deep Space Network. Their data still appears on scientists' screens, and their mission, a mission of discovery, endurance, and wonder, continues. They remind us that exploration doesn't always need a destination. Sometimes just going, just reaching, just listening, that's enough. Even in the fading light, they are beacons, and as long as they keep speaking, we'll be listening. In the chill of interstellar space, where the sun is just another bright dot and the background hum of the universe grows louder, Voyager 1 and Voyager 2 continue their long flight into the dark. But if you were to lean in close, very close, you might just hear the soft ticking of time catching up. Their power is fading, slowly, inevitably. Like old lanterns burning their final drops of oil, the Voyagers are beginning their long goodbye. From the very start, the Voyagers were powered by something quite special: radioisotope thermoelectric generators, or RTGs for short. These devices use the heat from decaying plutonium-238 to generate electricity. Unlike solar panels, which get increasingly ineffective the farther you travel from the sun, RTGs keep humming regardless of distance, a perfect solution for deep space missions. But even RTGs have a shelf life. Plutonium-238 decays at a steady, predictable rate, which means the power output has been decreasing year by year. At launch in 1977, each Voyager's RTGs generated around 470 watts of power, about enough to run a few light bulbs. It was modest even then, but it was stable and consistent. Today, nearly 50 years later, the output has dropped to less than half that, and it's still falling. What makes this particularly tricky is that Voyager isn't just a box with an on switch. It's a complex machine with many parts that all need power. Instruments, heaters, transmitters, memory systems, attitude control. They all draw electricity, and as the available power dwindles, choices must be made. Which systems are essential, and which ones can go dark? NASA's engineering team has been managing this balancing act with a mix of creativity, caution, and a little bit of magic. They've gradually turned off instruments one by one, not because the instruments themselves are broken, but because there simply isn't enough juice to keep them running. It's a bit like deciding which lights to turn off in your house during a power outage, knowing that eventually even the essentials might have to go. The process has been ongoing for years. Some instruments were shut down as far back as the late 1990s. Others have held on longer, transmitting data about magnetic fields, charged particles, and cosmic rays. Each time one is powered off, it's a small moment of mourning. Not dramatic, but deeply felt by the mission team. These instruments have been companions for decades. Each one that goes silent means a little less science, a little less conversation with the void. In 2023, Voyager 2's plasma science instrument was deactivated. That tool had been monitoring the density and temperature of particles in space, helping researchers map out the edge of the heliosphere and the conditions in the interstellar medium. Its loss was keenly felt but necessary. There simply wasn't enough power to keep it running alongside everything else. And it's not just about the science instruments. The spacecraft must also keep themselves warm. Interstellar space isn't just cold, it's bone-deep freezing, with temperatures nearing absolute zero. The RTGs produce some heat, which helps, but small heaters are strategically placed throughout the spacecraft to prevent key systems from freezing. Those heaters consume power too, and they're being turned off selectively. Some parts of the spacecraft are now operating well below their original temperature specifications, wrapped in layers of insulation, and held together by a combination of clever engineering and stubbornness. Then there's the transmitter, the system that beams data back to Earth. Keeping that signal alive is a priority, but even it is under threat. As power continues to drop, NASA will eventually face a final, heartbreaking decision: shut down the transmitter or shut down something else vital. At some point, there will be no more choices, only silence. But while the end is visible on the horizon, it's not here yet. Engineers have been finding clever ways to stretch the remaining power. One recent trick involved tapping into a small onboard voltage regulator that had never been used before, a sort of backup to the backup, just to reclaim a tiny bit of extra energy. It wasn't much, but it bought time. Time is the most precious resource Voyager has left, and even with their fading strength, the Voyagers are still sending valuable data. They're still contributing to our understanding of cosmic rays, solar influence, and the nature of space beyond the heliosphere. The quality of the data hasn't diminished, only the volume. Each bit of information takes longer to send, each packet is more carefully curated. But it still arrives, clean and sharp from billions of miles away. It's worth remembering that most space missions don't last this long. They're designed for months, maybe a few years. Voyager was expected to last 5 years at best. Its current age is a kind of engineering miracle. Not because it defied physics, but because it was built to last, and because the people who've maintained it never stopped caring. Behind the scenes, there's a small but dedicated team at NASA's Jet Propulsion Laboratory who monitor the Voyagers every day. They craft each command sequence with extraordinary care, double-checking every line of code before transmitting it across the solar system. At the current distance, it takes about 22 hours for a signal to reach Voyager 1, and another 22 to hear if it responded. Imagine trying to troubleshoot a problem with your car, but every message to the mechanic takes nearly 2 days. That's what the team deals with, day in and day out. They know the end is coming. They've made peace with it, professionally at least. Emotionally, it's harder. Some of these engineers have worked on Voyager their entire careers. Others inherited the mission from those who launched it, passing the torch from one generation to the next. There's pride in keeping the spacecraft alive this long, but also a quiet sadness in knowing that each fix is likely the last. Eventually, sometime in the next few years, the power output will fall below what's needed to run even the bare minimum systems. The transmitters will shut off. The spacecraft will go silent, but they won't stop moving. Long after their final signal fades, the Voyagers will continue drifting through the galaxy, still carrying their golden records, still holding the music, languages, and memories of Earth. They'll become ghost ships of humanity, gliding through the dark with no audience, no destination, and no expiration date. Their last sparks of power may be fading, but their legacy will glow for centuries, in textbooks, in documentaries, in the minds of everyone who looks up at the night sky and thinks, we sent something out there, and it's still going. Even at the edge of what's possible, Voyager teaches us that endurance matters, that small voices can carry across great distances, and that sometimes the quietest missions have the loudest echoes. Somewhere out there in the galactic dark, 2 golden records are spinning silently through space. Each one is bolted to the side of a small spacecraft no larger than a compact car, drifting ever farther from home with no particular destination. And if you let your imagination wander just a bit, which is highly encouraged at this point in the script, you might start to wonder, what if someone actually finds one? Not just a random cosmic collision or a curious rock. We're talking about someone intelligent, curious, capable of noticing this strange little object floating through the interstellar void, catching it, inspecting it, and eventually decoding the story it carries. It sounds far-fetched, and it is, but that's never stopped humans from dreaming. The golden record was never about high odds. Carl Sagan and his team knew that from the start. They weren't expecting a galactic pen pal. The likelihood of any civilization ever coming across one of the Voyager spacecraft is vanishingly small, Even though they're travelling at over 35,000 miles per hour, space is vast, unimaginably so. The galaxy is a neighbourhood where everyone lives millions of light years apart and nobody leaves notes on the fridge. But as a thought experiment, it's irresistible. So let's suppose that somewhere thousands or even millions of years from now, an alien civilization intercepts one of the Voyager spacecraft. What might they make of it? First, there's the obvious issue of discovery. These spacecraft aren't broadcasting. They're not blinking or beeping. By the time an alien civilization finds Voyager, its transmitter will have been quiet for a very long time. They'd have to spot it the old-fashioned way, as a cold, silent object glinting faintly in starlight, barely distinguishable from the background noise. Once found, though, it would stand out. The spacecraft itself is a bit of a mechanical time capsule, all wires and struts and angular elegance. But what would really catch their attention is that strange golden disc, mounted to the side and enclosed in a protective aluminum case. It's the extraterrestrial equivalent of finding a message in a bottle, except the bottle is made of metal and the ocean is about 98% empty. Now imagine some alien scientists back in their lab, cautiously unbolting the disc and discovering the engraved diagrams. There are instructions etched into the cover showing how to play the record, how to decode its images, and even how to find Earth using a map of pulsars. To us it all seems rather straightforward. To them, it might be the interstellar equivalent of assembling IKEA furniture without the manual. Puzzling, certainly, but fascinating. The diagrams include hydrogen atoms, mathematical constants, and timings of pulsars relative to Earth. Universal signposts that might be decipherable to any civilization with a grasp of physics. With some effort, they could figure out how to play the record and reconstruct the encoded images and sounds. And then the real fun would begin. What, exactly, would an alien make of Chuck Berry? Johnny Be Good is track number 11 on the Golden Record, a rollicking, joyful slice of 1950s rock and roll. To us it's iconic, but to a species with no ears, no cultural context, and possibly no concept of rhythm, it might come across as pure chaos. Fast, jangly, emotional, and utterly unlike anything in the natural world. They might love it, or they might assume it was a distress signal. The musical selections were deliberately diverse, with pieces from all over the planet. Bach, Beethoven, traditional Chinese guqin music, Aboriginal songs, Senegalese percussion, Bulgarian folk harmonies, and Louis Armstrong's melancholy blues. There's even a gamelan piece from Indonesia and a Navajo night chant. If nothing else, aliens would be able to tell that Earth was noisy, diverse, fond of repetition and pattern, capable of emotion, expression, and perhaps even something like art. And then there are the sounds. Real-world recordings stitched together into a kind of sonic collage. Ocean waves, wind, thunder, laughter, a kiss, a heartbeat, the cry of a baby, a galloping horse, the sound of a Saturn V rocket lifting off. One can only imagine the puzzled discussions among alien analysts trying to decode what any of that means. Do you think the high-pitched squealing represents communication? No, I believe that's what they use for emotional bonding. But what about the wet smacking sound? Possibly a nutritional ritual. And the whale? Definitely a philosopher. There's something both humbling and hilarious about the idea that a highly advanced civilization might one day sift through our auditory leftovers and try to reconstruct what kind of beings we were. They'd also encounter greetings in 55 human languages, from ancient Sumerian to modern Mandarin. Some are formal, some are cheerful. The English greeting is simple and sweet. Hello from the children of planet Earth. It's not technical, it's not poetic, but it's honest. That counts for a lot. And then there's the visual content, 116 images encoded on the record, showing a wide array of human life and nature on Earth. There are pictures of people eating, dancing, giving birth and holding hands. There are anatomical diagrams, shots of Earth's geography, animals, and even a blurry image of a supermarket aisle. All very ordinary to us, but to someone without context, they might look like the documentary footage of a bizarre carbon-based civilization that once flourished on a moist blue marble. One particularly poetic inclusion is the brainwave data of Andruyan, recorded while she meditated on the history of life and the experience of falling in love. To us, it's a moment of beauty frozen in electromagnetic patterns. To someone else, it might look like a series of erratic pulses and strange peaks. But who knows? Maybe they'll be able to decode not just the signal, but the feeling behind it. Of course, all of this assumes the finders are capable of, and interested in, interpreting the record. Maybe they're curious, maybe they're cautious, maybe they're so advanced that they glance at the record, shrug their appendages, and go back to harnessing dark energy to power their art galleries. Or maybe, just maybe, they'll listen. And in that listening, they'll hear the laughter of children and the songs of whales. They'll hear ancient greetings and spinning records, the whisper of wind and the hum of machines. They'll hear Earth, not as a collection of data, but as a living, striving, singing planet that once looked up at the stars and wondered, are we alone? It's not just about whether aliens will understand the golden record. It's about the fact that we sent it at all, that we chose to fill it not with warnings or weapons, but with back and blues and the sound of a heartbeat, that we believe someone out there might care enough to listen. In that sense, the message isn't really for aliens, it's for us. A declaration, frozen in gold, that says, this is who we were. We tried to understand. We tried to reach out. We made something beautiful, and we sent it into the dark. And even if no one ever finds it, even if the record spins through space untouched for 1 billion years, it still matters. Because it's out there, still drifting, still whispering, still hopeful. It's hard to imagine a space mission that lasted longer, travelled farther, or touched more hearts than Voyager. Launched in the late 1970s with a slide rule and a dream, these twin spacecraft weren't just explorers. They were ambassadors, archivists, and accidental poets. And while they continue to coast silently through interstellar space, their influence echoes loudly here on Earth. Voyager's legacy didn't end with its last planetary flyby. If anything, that's when its real impact began. It lit a spark, not just among scientists, but across the imagination of an entire planet. It's no exaggeration to say that Voyager changed how we think about space exploration, and it left footprints on the path that many future missions would follow. For planetary scientists, Voyager was a revelation. Before it, much of the outer solar system was a blur, fuzzy telescopic images and speculative textbooks. Voyager turned those question marks into high-resolution answers. Moons once assumed to be lifeless and inert were revealed to be geologically active. Ice-covered worlds hinted at hidden oceans. Magnetic fields twisted in unexpected directions. And rings, oh, the rings, turned out to be everywhere, fragile and complicated and dynamic. All of this redefined what counted as interesting in the solar system. For decades, Mars had held most of the scientific spotlight. Voyager widened the stage. Suddenly, moons were in the running for life's potential habitats. Atmospheres were more exotic, planetary weather more extreme. There was more to see, more to wonder about, and much more to explore. And explore we did. Missions like Galileo, Cassini, and Juno didn't just follow in Voyager's footsteps, they stood on its shoulders. Galileo orbited Jupiter and dove into its storms, building on Voyager's data to study the planet's interior and its bevy of strange moons, especially the now infamous Europa. Cassini, with its dramatic ring dives and poetic finale, was directly inspired by Voyager's discoveries at Saturn. It even carried its own small golden record, a tribute tucked into the spacecraft's software, and provided the long, slow answers to the questions Voyager first asked. Cassini didn't just look at Titan's atmosphere, it dropped a lander into it. It didn't just admire Saturn's rings, it mapped their structure in exquisite detail. Then came Juno, a spacecraft designed to probe beneath Jupiter's clouds and untangle its magnetic mysteries. Juno's designers used Voyager's gravity assist playbook and refined it with modern tools. Voyager had cracked open the treasure chest. Newer missions dug through it with tweezers and microscopes. Even missions to other targets, like New Horizons at Pluto, drew on Voyager's legacy. New Horizons was sometimes nicknamed Voyager 3, not because it was officially part of the family, but because its spirit was the same. A single-shot flyby. An encounter with a world we'd never seen up close. A moment of awe. Voyager also set new standards for what long-duration missions could look like. It showed that, with good engineering and a bit of luck, a spacecraft could remain operational not for months, but for decades. That changed how agencies thought about planning, funding, and maintaining missions. It also changed how scientists thought about their own careers. A student just starting out in the 1980s could work on Voyager their entire life, and some did. But Voyager's legacy isn't confined to labs or launch pads. It also punched its way into pop culture, not with the loud splash of a blockbuster, but with the quiet ripple of something deeper. It showed up in films like Star Trek, the motion picture, where a fictionalized Voyager returns to Earth, transformed into a sentient being. It was referenced in countless documentaries, books, and songs. It became a metaphor for persistence, for exploration, for humanity's quiet courage to look outward. The Golden Record alone became a cultural icon. It's been recreated in museums, parodied on television, and celebrated in music. Artists have sampled its audio. Writers have used it as the seed for stories about alien contact, lost civilizations, or humanity's future descendants discovering their own ancient messages. More than anything, Voyager became a symbol, not of triumph exactly, but of wonder. It didn't explode across the sky like Apollo or land like a dusty hero like the Mars rovers. It just kept going. A tiny whisper in the dark, a vote of confidence in the long view. The spacecraft themselves, simple as they seem now, were engineering marvels, built with 1970s technology, hand-soldered circuits, analog tape recorders, and computers with less memory than a modern calculator. They've outlived most of the people who designed them. They don't carry AI. They don't adjust course with onboard intelligence. They were built for durability, not agility. And yet their endurance has outshone almost everything else we've launched. Their very design has become legendary in engineering circles. Every antenna, every protective shield, every line of code was optimized for a mission that was never supposed to last this long. And yet, the Voyagers are still making discoveries, still sending back data from regions no spacecraft has ever travelled before. Voyager also reshaped our philosophical understanding of exploration. It wasn't just about reaching new places, it was about asking better questions. What is the shape of a planetary magnetic field? How does solar wind interact with interstellar space? What happens at the boundary between our star's influence and the wider galaxy? These were once the domain of theory. Now, thanks to Voyager, we have data, and while the spacecraft are too far away now to receive new commands reliably, they're still being watched, still being tracked, still being loved. NASA's mission team, a mix of grizzled veterans and fresh-faced engineers, continues to nurse them along, turning off systems strategically, rerouting power with care, and coaxing one more transmission from the void. Even the way we talk about Voyager has changed. It's no longer just a probe. It's become a kind of cosmic poet, carrying humanity's dreams across the stars. Not loudly, not boastfully, but persistently, patiently, with that same quiet strength that marks our best stories. And perhaps that's the real legacy of Voyager, not just what it discovered or where it went, but what it reminded us about ourselves, that we are a species that asks questions, that we build things not just to use but to understand, that we sometimes make art not for fame or profit, but because it feels right to send music to the stars. Voyager's journey has been a slow unfolding, a message in a bottle not meant to be answered, but simply to be cast into the sea, because sending it said something meaningful about the ones who did. As long as the Voyagers are still drifting, still sending, still spinning their golden records through the dark, a piece of us is out there, not searching for recognition, but quietly carrying the legacy of wonder. A legacy written not in ink, but in photons, in pulses, in patience, and in the enduring belief that it is always worth reaching out, even into the unknown, out there, beyond the planets and the cold breath of the heliosphere. Two spacecraft continue their long, slow journey. No destination, no course corrections, just a quiet drift through the deep night, further than any human-made object has ever travelled. Voyager 1 and Voyager 2 are still out there, still travelling, still listening. They're old now, by any standard. They were born in a world of rotary phones and disco balls, handwritten code and slide rules. They launched when some people were still convinced that Pluto was the final stop on our cosmic tour. They've flown through solar flares, radiation belts, and the ever-thinning edge of the sun's influence. They've seen worlds we once only guessed at, and sent back evidence of geysers, volcanoes, rings, oceans, storms, and magnetic madness. And now, with just a few instruments still warm, they continue into the vast silence. But it isn't really silence they move through. It's just too quiet for ears to notice. The space beyond the solar system hums with charged particles and ripples of ancient starlight. It's a place where atoms drift for eons without meeting, where distance loses all practical meaning, and where time itself stretches out like a road without signs. And yet, in the middle of all that quiet, something human is there, a piece of us, wrapped in metal and gold, humming softly with fading power and carrying a message we wrote long ago. It's easy to forget how extraordinary that is. We built these spacecraft to explore the outer planets. That was their job, their assignment, their scope. But the moment they passed those final planetary encounters, they became something more. Not because they changed, but because we did. We realized they were no longer just tools. They were storytellers, pilgrims, time capsules, cosmic postcards with no return address. Voyager's journey is in many ways a metaphor for what it means to be human, to ask questions that have no clear answers, to build things that will outlive us, to wander not for profit or conquest, but for curiosity, for the sheer joy of seeing what's out there. The spacecraft aren't fast, they're not flashy, they're not built to impress, but they persist, and there's a quiet dignity in that. Even now, long after their cameras have gone dark and most of their instruments have been switched off, they still speak. Their signals are faint, weaker than a whisper from across a continent, but they arrive, steady and disciplined. The same tones that once relayed images of volcanic moons and icy rings now carry information about the density of interstellar plasma and the direction of the magnetic field lines beyond the sun's grasp. It's not glamorous data, perhaps, but it's pure gold to the scientists who listen for it. And in that listening there is something sacred. Because listening is an act of hope. It says we believe there is still something to learn, still something worth hearing. That even when the world is noisy and the night is long, a quiet signal from a distant place matters. Maybe that's the heart of Voyager's story. It never shouted. It never demanded attention. It just kept going. It taught us that wonder doesn't always arrive with a bang. Sometimes it comes pixel by pixel, bit by bit. A tiny dot on a screen that turns out to be a moon we never knew existed. The golden record bolted to each spacecraft's side was a final gift, not to science, but to imagination. We didn't have to include it. There was no scientific requirement to send whale songs and greetings in Sumerian. But we did it anyway, because we hoped someone, someday, might find it. We hoped it would matter. And even if it never is found, it still mattered. Because the act of sending it, of choosing to say hello before anyone else did, revealed something essential about us. The stars have always been silent, but we spoke first. We sent music, laughter, the sound of footsteps, the crackle of thunder, the roar of rockets and the hush of breath. We sent data and diagrams and the brain waves of someone in love. We didn't send warnings. We didn't send threats. We sent wonder. Because that's what we are. A species of questions and lullabies, of equations and lullabies, of curiosity and courage. Voyager's legacy isn't just about what it found. It's about what it inspired. New missions, new scientists, new dreams. It helped us realize that even our most distant machines can be storytellers. That even a spacecraft can carry meaning far beyond its mass. And that the farther we reach, the more we understand what it means to be home. One day soon, Voyager's power will finally run out. The signal will fade, the instruments will fall silent. No one will notice immediately. There will be no explosion, no dramatic farewell. Just a long pause in a signal that never resumes. But even then, the spacecraft will not be lost. They will keep moving slowly and steadily among the stars, silent but not forgotten. And someone, perhaps us, perhaps not, might remember that we once built 2 small ships and sent them into the dark not for answers but for the joy of the question. And maybe that's all the legacy we need. Now, as we reach the end of this story, I want to ask you what I asked when we began. Are you still awake? Still drifting among the stars with me? Or have you already slipped off into sleep, Voyager's gentle signal carrying you toward dreams? Either way, thank you for joining me on this quiet journey. Before you go, I'd love to hear where you're listening from and what time it is where you are. Whether you're under a city skyline or curled up in a quiet countryside, whether it's midnight or just the edge of dawn, thank you for being part of this moment. And if you've enjoyed this voyage through time and stars, consider leaving a like and subscribing to The Sleepy Scientist. It helps more dreamers find their way here and helps keep the signal going just a little longer. Till next time, rest well, stay curious, and remember, we spoke first.